How are you all doing this morning?
Pretty well.
Good to hear. So today we're going to be talking about mesh analysis. It is the complement to nodal analysis, which we discussed on Tuesday, and it is a means by which to solve circuits using multiple applications of Kirchhoff's voltage law. So let me share my screen. Get rid of all this stuff from circuits too. All right. Mesh analysis is typically the circuit analysis method that most students prefer. I think it's because the math is just a hair easier. So let's start with the following circuit. Where we have an 8-volt source here on the left. A 14 ohm resistor here. A 12 ohm resistor. I'm going to go ahead and get a dependent source into the mix. I'm going to say that this is 3/2 IX. There's a 22 ohm resistor. A 5 ohm resistor. And a 10-volt source, positive polarity on bottom. So we're going to develop an algorithm just like we did in the last class, whereby we'll figure out how to use mesh analysis kind of step by step. And if you do everything in this particular order, you should find that mesh analysis is, again, a very powerful tool, but also a very easy tool to use for circuit analysis. So I'm going to say that our current IX that controls our voltage source is here, the current through the 12 ohm resistor, direction down. And my ultimate goal in this particular problem is to find the power supplied by our dependent source. So the first step of mesh analysis is to identify our meshes. Do any of you guys remember from our first lecture what a mesh is?
Vaguely.
Vaguely. All right. Well, what a mesh is any loop which does not contain a smaller loop. So in this case, I'm going to say that this is a mesh. This kind of window pane thing here is a mesh. And this guy is a mesh as well. And I've drawn arrows on these meshes, which is going to bring me to step 2, where we label our mesh currents. So I'm going to call this mesh current here, I1. And so what I mean by a mesh current is this is a current that's circulating around this loop in the direction of the arrow that I've indicated. So it's flowing clockwise around this left-hand most part of the circuit. I'm going to call this guy in the middle I2, and so we have a current flowing clockwise around this middle portion of the circuit. And then over here, I'm going to call this guy I3, and we have a current flowing clockwise around the right-hand portion of our circuit. So I want you guys to pay attention to something here real quick. If we look at, say, the 12 ohm resistor or the 22 ohm resistor, for instance, there are actually two mesh currents flowing through those elements, right? So there is a mesh current I1 flowing down through the 12 ohm resistor, and there's a mesh current I2 flowing up through the 12 ohm resistor, as each of those currents make their way around their clockwise paths. This is going to be very important for us to notice when we write our Kirchhoff's voltage law equations, which is actually going to be our next step. So let's look at mesh 1. Our goal here is to write a Kirchhoff's voltage law equation where we express all of the voltage drops across our resistors in terms of our mesh currents. So if we start at the bottom left-hand corner, which is where I like to start, we first see a the negative polarity terminal of an 8-volt source. So our equation is going to look like negative 8 volts plus, then I'm going to have 14 ohms, my resistance, times I1, because the voltage drop across that 14 ohm resistor using Ohm's law is simply the resistance value multiplied by the current flowing through it. When we get to the 12 ohm resistor, we're going to see something similar. 12 ohms, the resistance value, but the total current that flows through the 12 ohm resistor is I1 minus I2. We're going to set this guy equal to 0. So let's talk about this I1 minus I2 concept, okay? We're following mesh 1 around its clockwise path. When we get to the 12 ohm resistor, and so when we follow mesh 1 around its clockwise path, or current I1 around its clockwise path, we should observe that the current I1 is always associated with a positive sign. When we get to the 12 ohm resistor, because I2 is flowing in the opposite direction as I1 through that particular branch, that is where that negative sign comes from. So when we write our KVL equation for mesh 2, starting at the bottom left-hand corner and following our mesh current I2 around its path, now we are going to see 12 ohms. And since we're following I2, it's going to get the positive sign, and that current I1 is in the opposite direction. So now we're going to have I2 minus I1. Then we see the positive polarity terminal of our dependent source. So that's going to be 3/2 IS. See our 22 ohm resistor. And we're going to have I2 minus I3 and set this guy equal to 0. So any questions about how I developed that KVL equation for mesh 2?
How did you get the 3/2, 3/2 IX?
So that's a voltage source, right?
Oh, yeah, it's given.
Yeah, a dependent voltage source whose voltage is given to be 3/2 Ix. So that's where that guy came from. Any other questions? All right, then let's move along to mesh 3. So starting at the bottom left-hand corner, I see my 22 ohm resistor. And now, since I'm following I3 around its path, it'll be 22 ohms times I3 minus I2. Then I have a 5 ohm resistor. The only current flowing through it is I3. And lastly, I see the negative polarity terminal of the 10 volt source. So I'm going to have minus 10 volts is equal to 0. And because I have a dependent source, I'm going to have to write an equation for the controlling variable. So I'm going to write an equation that expresses Ix in terms of my mesh currents. So let's look at our circuit diagram. Ix is the current flowing down through the 12 ohm resistor. So how we are going to express this in terms of our mesh currents is that since I1 is in the same direction as Ix, it will get a positive sign. And I2, the other mesh current that's flowing through that 12 ohm resistor, since it's flowing opposite the direction of Ix, will get a negative sign. So Ix is simply I1 minus I2 for this particular circuit. Does everybody understand why it works that way? I can talk about it again if I need to.
I think I understand it.
All righty. So with that in mind, we could substitute in that relationship and come up with a simplified set of equations, which we can easily put in our calculator. So let's organize our equations. So our first equation, we have 12 ohms plus 14 ohms times I1. We have negative 12 ohms times I2. We have 0 times I3. And we're going to set this equal to positive 8. For our second equation, which has that Ix in there. So I can see that there's a 12 for sure, a negative 12 actually. So let's put that in as a coefficient of I1. And now we have this 3/2 Ix, where Ix is I1 minus I2. So we're also going to have a coefficient of positive 3/2. And because this is a voltage representing the voltage controlled current source, excuse me, a current controlled voltage source, this is going to have units of volts per amp, which is the same thing as an ohm. So it's going to get multiplied by I1. For I2, we're going to have positive 12. We're going to have positive 22. And we are going to have negative 3/2. Finally, for I3, our coefficient is negative 22 ohms. And we have no constant terms in this equation, so we set it equal to 0. And finally, for our last equation, we have no I1, negative 22 I2, and positive 22 plus positive 5 I3, and it will be equal to 10 volts. So we have 1, 2, 3 equations with 3 unknowns. So now we can solve our equations. So I'd like for you guys to throw this system into your calculator and tell me what the values for I1, I2, and I3 are.
I got I1 equals 2 amps.
2 amps.
Actually, I think I might be wrong. I got all of them to be equal to 2. Maybe I entered a few of the coefficients wrong. So
Yeah, that I didn't get 2 for any of them. So
okay.
did anybody else get something?
I got 0.85 amps for I1.
What did you get for I2?
1.17 amps.
And finally, I3?
1.3235 amps.
All right, so that's what I got. So I'm going to assume that between the two of us, we got it correct there. So we know what our mesh currents are, but that doesn't finish the problem, right? Because we were asked to determine the power supplied by our dependent source. So let me ask you guys a question. Based on what we know about our mesh currents, or the fact that we know all of our mesh currents now, can we find that power pretty easily? So I would say that the power supplied by our dependent source is going to be the voltage drop across our dependent source. I'm going to call that VDEP times the current IDEP flowing into the negative polarity terminal, right? So I'm going to call this guy right here IDEP. I'm going to call this voltage VDEP. I can see that VDEP, the voltage drop, is just 3/2 IX. So that's going to be 3/2 times my mesh current I1 minus my mesh current I2, because I already know that IX is mesh current I1 minus mesh current I2. So how is I dependent related to our mesh currents?
Will that not be I3 minus I2?
So I3 minus I2 is the current flowing up through the 22 ohm resistor. I'm looking for the current that is flowing from the right to the left through the dependent source. Let's see what chat says. Why is it I1 minus I2? Why is what I1 minus I2? Why is IX I1 minus I2? Is that your question, Taj? All right. So I will re-explain that. If we look at where IX is defined here, it is the current flowing down through the 12 ohm resistor. Can we agree on that?
Yes.
All right. So when we're following I1 around its clockwise path, it is flowing down through that 12 ohm resistor. And we also have a current of I2 flowing up through that same 12 ohm resistor. So since there are two mesh currents and they're flowing in opposite directions, IX has to be the current that is the difference of those two, where we take the one that's flowing in the same direction as IX to be positive and the one that's flowing in the opposite direction of IX to be negative. So that's why we get IX is equal to I1 minus I2. So let's circle back around and kind of do something similar for this current I dependent, all right? So I dependent is the current flowing from right to left through the dependent source. Well, as I2 makes its clockwise path, it is the current flowing from the left to the right through that dependent source. So I would argue that I dependent is simply negative I2. Does everybody understand why that is?
Somewhat.
So the mesh current is the current flowing around that loop, right? For that branch that contains only the dependent source, that's the only current flowing in that portion of the loop. And it is flowing from left to right because of the way that I've drawn my mesh current arrow. Are we okay with that statement?
Yeah.
Why did you define I dependent as going from right to left into the dependent source?
Okay, so that's a fantastic question. Because I am trying to find the power supplied by my dependent source, I need my current to flow into the negative polarity terminal.
Okay,
Because
thank you.
voltage drop times the current flowing into the negative polarity terminal gives me the power supplied by that source.
Okay.
So if we can agree that as the current I2 flows around its clockwise path through the portion of the circuit that has the dependent source, it is flowing from left to right. And we can see that I dependent is the current flowing through that dependent source from right to left. Those two currents have to have the same magnitude but opposite signs because they're representing the same current flowing from opposite directions. So that is why I am saying that I dependent has to be negative I2. So with that in mind, I can now easily solve for the power supplied by my dependent source, right? So I'm going to have 3 halves times I1, which is 0.848 amps, minus I2, which was 1.170 amps. And then I'm going to multiply this quantity by negative 1.170. And I get a power of 0.565 watts. Are there any further questions on this problem? And I'm happy to answer them if there are.
So just to like clarify, I dependent is negative because it's the same as I2, but it's flowing into the negative terminal or negative part of the dependent source, right?
No. I dependent is negative I2 because it's flowing in the opposite direction of I2.
Okay.
Right. So this goes back to what we talked about on our very first lecture. So let me draw a little something here. So if I have a generic circuit element, and I say that there is a current of 5 amps flowing down, that is the exact same thing as me saying that there is a current of negative 5 amps flowing up. That's the exact same situation we have for our dependent source. It's just oriented in a right to left configuration. Any other questions regarding this particular problem?
So it's up to you to decide whether right is positive current and left is negative, but whatever you decide, you have to be consistent.
So
Or is it based on the circuit diagram? Like you have the 8 volts and you decided to go positive up, negative down, and you flipped it on the other side for the 10 volts.
So the choice I made here was whether my mesh currents were clockwise or counterclockwise. Okay. I chose to have them all go clockwise around their individual meshes. It does not matter if we choose them to go all clockwise or all counterclockwise or some combination of clockwise and counterclockwise. So I want to rework this circuit where I'm going to mix things up, and I will show you that we will get the exact same answer. All right. Just to prove to you that it really doesn't matter. So let's do it down here. We're just going to solve for our mesh currents, because if we get the exact same answers there, then obviously everything else will work itself out. So let me redraw my circuit. And we'll get some I'm going to call on you guys to help me write my equations, all right? So here's my 8-volt source. Here's my 14 ohm resistor. Here is my 12 ohm resistor. Here's my dependent source, providing me 3/2 IX amount of voltage across the terminals of that guy. Then I have my 22 ohm resistor. Here is my 5 ohm resistor. And here's my 10-volt source. And then I just have that common line down here at the bottom. All right. So identical circuit to the one we just analyzed, where I'm defining IX as the current flowing down through the 12 ohm resistor. So we're starting with the exact same circuit. Now I'm going to choose that my mesh current I1 still flows in that clockwise direction. And I'm going to say that I2 is going to flow counterclockwise. and I3 will flow clockwise. All right, so I've labeled my mesh current, or excuse me, I've identified my meshes and labeled my mesh currents kind of all in one step, which is probably how I'm going to do it from here on out. So at this point, I should start writing my KVL equations. So let's look at KVL at mesh 1. So I'm going to start in my bottom left-hand corner, and I'm going to follow mesh current I1 around its clockwise path. So I see negative 8 volts first. Then I see the 14 ohm resistor. And the only current flowing through the 14 ohm resistor is I1. So I just multiply 14 times I1. Next, I see my 12 ohm resistor. And it has a current of I1 flowing down through it, because as we follow I1 around its clockwise path, it's going down. But as we follow I2 around its clockwise path, it's also going down. So that means that we're going to have 12 ohms times I1 plus I2 this time. And set this equal to 0. When we get to KVL at mesh 2, we are going to follow current I2 around its clockwise, or excuse me, counterclockwise path, okay? So we're going to start from the bottom left-hand corner and follow it around. So the first thing that we're going to see now is the 22 ohm resistor, where we're going to have a current of I2 flowing up through the 22 ohm resistor and a current of I3 also flowing up through the 22 ohm resistor. So let me explain that. Right. So around this portion of its path, I2 is flowing up. Around this portion of I3's path, it's also flowing up. They're in the same direction, so the currents need to add together. The next thing that we are going to see is the negative polarity terminal of the dependent source. So that's going to be negative 3/2 IX. And then finally, we are going to see the 12 ohm resistor. And we are going to see that I2 is flowing down and I1 is also flowing down. So we're going to have I2 plus I1. Set this guy equal to 0. Finally, our last KVL equation at mesh 3. We see the 22 ohm resistor first, I3 and I2, or so we have I3 and then I2 is flowing in the same direction, so we add them. Then we see the 5 ohm resistor. The only current flowing through it is I3. And lastly, we see the negative polarity terminal of our 10 volt source. So we subtract 10 volts and set it equal to 0. So now I'm going to organize my equations. So I have 14 ohms plus 12 ohms. So I'm just going to say 14 plus 12 is 26 ohms multiplied by I1. Then I have positive 12 ohms times I2. And 0 times I3 is equal to positive 8. For my second mesh current, I have 12 ohms multiplied by I1. And then I have -3/2 Ix. So I guess we forgot to do something here. So let's take care of it right now. Our other equation is expressing Ix in terms of our mesh currents. Well, we can see now that Ix is I1 plus I2. So we have -3/2 Ix. So that's going to be -3/2 I1. Our coefficient for I2 is going to be 22 plus 12. So that's going to look like 34 ohms. But we also have -3/2 Ix. So we're going to have -3/2 I2 from that. So -3/2 per amp. This guy gets multiplied by I2. And we have plus 22 ohms times I3 equal to 0. So let me just double check this guy real quick. My coefficient for I1 is 12 minus 3/2. That checks out. My coefficient for I2 is 22 plus 12, which is 34, minus 3/2. So that checks out. And then my coefficient for I3 is just positive 22. All right. For our last equation, we have 0 I1 we have 22 ohms times I2. And then we have 22 plus 5 is 27 ohms. Make sure that looks like a 2. That made it look even more like a 1. I apologize. 27 ohms. I3 is equal to positive 10 volts. So here is our system. I'm going to throw this guy into my calculator. So I have 26, 12, 0, 8, 12 minus 3/2, 34 minus 3/2, 22, 0, 0, 22, 27, 10. Solve, and I get I1 is equal to 0.848 amps. I2 is equal to negative 1.170 amps. And I3 is equal to 323 amps. So I got the exact same answer as I did previously, except that I2 now has a negative sign. So it has the exact same magnitude, but it's got a negative sign because I defined it as flowing in the opposite direction. So with that being said, it absolutely does not matter in which direction you choose to have your mesh currents flow, whether they be all clockwise, all counterclockwise, or some combination thereof. I will say that combining clockwise and counterclockwise gets messy quickly. So I would personally either pick all clockwise or all counterclockwise and then just stick with that. I can literally never see a benefit of mixing them up. It will work, but it's confusing. So I feel like you're more likely to make mistakes doing that. I personally always choose to have my mesh currents flowing in a clockwise direction. Regardless of how the circuit is laid out, I make my mesh currents flow in a clockwise direction. That being said, I know a lot of students who make their currents flow in a counterclockwise direction because that is the same direction that they're used to drawing their moment of inertia arrows in their statics classes and stuff like that. It literally doesn't matter to me at all which convention you choose. Any other questions on this particular problem?
No, sir.
All right. So let's mess things up by introducing a current source, right? Our previous problem didn't have any current sources at all. And we are going to see that when we have a current source, things are going to get a little bit wonky. So the problem that I would like for us to analyze is this guy. No dependent sources on this one. We have a 5-volt source here. An ohm resistor. Here we will have a 40 ohm resistor. Ohm resistor. And I'm going to put a current source here in the middle of the circuit. Put another 30 here. 40 here. Oops. Sorry, I meant to put another 10 ohm resistor down here. All right, so this is our circuit of interest. I want to know the power supplied by the 5-volt source and the power supplied by the 3-amp source, okay? So in a single step, I'm going to identify and label my meshes. I'm going to say that this guy is mesh 1. And this is actually typically how I draw my arrows, just a small circle with an arrow letting me know what direction the current's flowing through. I'm going to say that this guy, this mesh in the top right is mesh 2. And this guy on the bottom right is mesh 3. So let's start by writing a KVL equation for mesh 1. I'm going to start here and I'm going to follow mesh current I1 around its clockwise loop. So somebody on Zoom, tell me, what do I see first as I follow that current around its clockwise path?
Negative 5 volts.
Negative 5 volts. Thank you, sir. What do I see next?
10 ohms times I1.
All right. What's next?
40 ohms times I1 minus I2.
Absolutely correct. And what's the, sorry, what next?
Then it'd be 30 ohms times I1 minus I3.
And the last thing I see as I return to that bottom left-hand corner?
10 ohms times I1.
All right. Everybody okay with that mesh equation? Sorry, I couldn't see your name, whoever did that, but you did an excellent job. Every single part of it is correct. So when we do KVL around mesh 2, we are going to run into a problem. All right, and so let me explain what I mean. If we start at the bottom left-hand corner, the first thing that we're going to see is our 40 ohm resistor and a total current of I2 minus I1 is going to pass through it. Nothing difficult there. Then we see our 30 ohm resistor, and the only mesh current that's passing through it is I2. Then we see a current source, right? Now we are doing Kirchhoff's voltage law. And this is an independent current source, which means that the amount of current flowing through it has nothing to do with the voltage drop across it at all. So we can't really do anything here other than say that this is going to be, well, let me put it in this green color. I could call it positive polarity over here, negative polarity over here, V 3 amps, right? I could call it that for whatever reason. And so I can say plus V 3 amps is equal to 0. I cannot simply ignore it, right? It is a current source. There may be a voltage drop over it. So there is no reason whatsoever for me to assume to just ignore it, because that would imply that I know that there is 0 volts across it, and I cannot do that. When I write my equation for mesh 3, I'm going to run into a similar issue, right? So starting at the bottom left-hand corner, I'm going to see 30 ohms times I3 minus I1. Now I see the negative polarity terminal of that V3A, so that's really all that I can do. And then I see my 40 ohms times I3, and I set it equal to 0. Okay? So I have a problem here, inasmuch as I have 3 equations and 4 unknowns. So I'm going to do something similar to what I did with the concept of a supernode in the last class, all right? So whenever I have an interior current source, and so that means that it is a current source on the inside of the circuit as opposed to the perimeter of the circuit, I am going to form what is called a super mesh. And so what that means is I'm going to create the smallest possible loop that contains that current source in the middle. So this is the smallest possible loop that satisfies that. And so what I'm going to do now is I'm going to apply Kirchhoff's voltage law around this loop. So doing this super mesh thing, it allows me to not take that path that caused me issues and introduce that extra variable. KVL around super mesh, and I'm going to call it 2, 3 because it contains meshes 2 and 3. So I'd like for somebody to tell me what this equation is going to be. Start here and just follow that purple path clockwise around where I've drawn. Tell me what I'm going to have.
I have a question.
Sure.
So since both currents are flowing in the same direction, would you just add them together in this configuration?
Okay, so
Or
that's a fantastic question. Okay, so we're still using mesh currents I1, or excuse me, I2 and I3 to describe what's going on here. We're not saying it's one big mesh current. So for instance, if we're looking at the 30 ohm resistor, we're going to have, or if we're looking at this 30 ohm resistor, because there are 2 of them, we are going to see that a mesh current I3 is flowing in the same direction as the purple path, and a mesh current of I1 is flowing in the opposite direction. So our first term would be like sorry, 30 ohms I3 minus I1. Then our next element is the 40 ohm resistor, where we have a mesh current of I2 flowing through it and a mesh current of I1, right? So tell me what's going on with the 40 ohm resistor.
40 ohms times I2 minus I1.
Exactly right. What do we see next?
We see the 30 ohm resistor,
And what current's flowing through it?
just I2.
Absolutely. And lastly, we see
The 40 ohm resistor,
with a current of,
I3 minus I2.
so it's this guy right here, right? He's on the outside edge of the circuit, so the only current that can flow through him is I3.
I3, correct.
So that initial question was an absolutely fantastic one, right? So we're not just lumping I2 and I3 together in one as one big current by any stretch of the imagination, because we have no reason whatsoever to do that. When we apply this super mesh technique, we are just writing a path and then writing a Kirchhoff's voltage law equation around that path. Now, let me erase this purple thing that I scribbled over here real quick. It is not a coincidence at all that our super mesh Kirchhoff's voltage law equation is exactly what we would get if we added these two guys together, because that is exactly what we are doing. We are effectively doing KVL around mesh 2 and KVL around mesh 3, and then adding those results together because we know that that unknown voltage drop across that 3 amp source is going to be positive when we go one way and negative when we go the other. So it's going to cancel each other out. So this is another instance of us effectively saying 0 plus 0 is equal to 0. So let me recross that guy out. Those guys out. So we have one equation here, two equations here. So we now have a situation, just like we had a little moment ago, where we don't know what, we have one more unknown than we have an equation. So our last thing that we can do is create a current relationship equation. Okay. So effectively, anytime that we have a current source in our circuit and we are trying to apply mesh, that current is in terms of our mesh currents. So what I mean by that is I can say that 3 amps, which is the current that is supplied by my current source, is going to be I3, because I3 is in the same direction as the 3 amp source as it goes through its clockwise path, minus I2, because I2 is in the opposite direction of the 3 amp source as it goes around its clockwise path. So 3 amps is equal to I3 minus I2 is our third equation. Now we can organize things and then solve our system, right? So the coefficient for I1 is going to be 10 plus 40 plus 30 plus 10. So that's 20 plus 70 is 90 ohms times I1. And then we have minus 40 I2 minus 30 I3, and that will be equal to positive 5 volts. So that's equation 1 reorganized. Now we'll reorganize our our super mesh equation. So we have negative 30 and negative 40 is negative 70 I1. 40 plus 30 is positive 70 I2. 30 plus 40 is positive 70 I3. And all of these guys together equal 0. Our third equation, we have 0 times I1 plus negative 1 times I2 times I3 is equal to positive 3 amps. And we solve this system. So take a couple of minutes and tell me what your results are.
I got minus 0.18 amps for I1.
Negative 0.18 amps. Okay, what did you get for I2?
Negative 1.59.
Alrighty, and what did you get for I3?
1.41 amps.
So that is exactly what I got as well. So I'm going to assume that we are both correct. So let's revisit what we were asked here, all right? The power supplied by the 5 volt source. Let's talk about that guy real quick because that's an easier question to answer. The power supplied by our 5 volt source is the voltage drop across our 5 volt source. That's easy enough. That's 5 volts. And the current flowing into the negative polarity terminal. Well, what's the current flowing into the negative polarity terminal of our 5 volt source?
I1.
I1, absolutely right. So we would simply have 5 volts times negative 0.18 amps, which is going to be negative 0.909 watts. All right. What does it mean that the power supplied by the 5 volt source is negative? So what does it mean in general if I have something supplying negative power?
It's absorbing that power rather than supplying it.
Exactly right. So in this case, the 5 volt source is absorbing power from the system, which means the 3 amp source is the one that's actually doing the supplying here, right? So we can absolutely have systems where our sources behave in a way that we don't expect as long as everything balances out. So for the power supplied by the 3 amp source, excuse me, this one is going to be a little bit trickier. We obviously know what the current is, but finding the voltage is going to be a little difficult. And it's a very, very small amount of difficulty if we think about things, okay? So I'm going to define the voltage drop across my 3 amp source where the current is flowing into the negative polarity terminal. And oh, what do you know? I've actually already done that. Where I have written negative V3A and then a plus sign is exactly me defining the voltage drop across my 3 amp source, with the current being supplied by my 3 amp source flowing into the negative polarity terminal. Everybody okay with that?
Yes.
All right, so now what we would have to do to solve for that particular voltage is write a KVL equation around just mesh 2 or mesh 3 and then solve for that voltage, which we already have those equations written right here. So now that we know those mesh currents, solving for that voltage V3A is trivial. So somebody take a moment and tell me what it's going to be. So has anybody gotten an answer for V3A yet? And if we look at this guy, we know what I2 is, we know what I1 is, we know what I2 is. So that V3A thing is the only unknown quantity. Or we can use the other relationship where we know what I3 is and we know what I1 is. So the only unknown is V3A. So that's a simple one equation, one unknown thing that you need to be solving.
I got for the top relationship, I got 99.07 volts. I'm not sure if that's correct though.
That is not what I got.
Okay.
So let's use the bottom relationship here real quick, right? Because we have negative V3I on one side, so we can literally just move it over to the other side. So we could say that our V3A is 30 ohms times I3, which is 1.409, minus I1, which is negative 0.182, plus 40 ohms times I3, 1.409, and I get, oops, don't know what happened here, 104.09 volts times 3 amps. If I did it with the first equation, so if I said that I had 40 ohms times I2, which was negative 1.591, minus I1, so minus negative 0.182, plus 30 times I2, negative 1.591. I get negative 104.09, which makes sense because when I move that V3A to the other side, I'm going to get negative V3A. So regardless of which of those two equations you use, if you're doing your algebra correctly, you should be getting 104.09 volts multiplied by 3 amps gives us a total power of 312.9 0.273 watts. So this problem was definitely a little bit trickier than the last problem because it has a current source in there, right? So doing mesh analysis with current sources present can be tricky because we have to not necessarily bend the rules, but extend the rules to accommodate for the fact that there is a current source that we can't write a KVL equation over. So I would like, unless there's any questions, I would like to work one more problem where we have a current source on the perimeter of the circuit and see how that messes with things. So any questions before we move along to one final example problem? All right.
So,
Sorry, what were you saying?
saying I don't think so.
Okay. All right, so let's look at this last guy. This is one that I have intentionally made tricky. Now you may be arguing, well, the last two seem pretty tricky themselves. This one more so. So this is our circuit of interest. We have a 5 ohm resistor. A 16 ohm resistor. A 20 ohm resistor. Here's a 25 ohm resistor. Here is a 21 ohm resistor. Here is a 7 amp source. And my goal in this problem is to determine this voltage that I've labeled here, Vx. And we are going to do this using mesh analysis, okay? So I'm going to identify my meshes and label them. So I'm going to call this guy mesh 1, this guy mesh 2, and this guy down here mesh 3. So somebody tell me what my KVL equation for mesh 1 is going to be. Starting at the bottom left-hand corner and following our path around that loop.
Why is Vx just right there in the middle?
Because I chose it to be. I want us to find that voltage, right? A voltage is defined as the difference in electric potential between 2 points in a circuit. So I chose 2 points in a circuit. I assigned one a positive polarity terminal, the other a negative polarity terminal, and so therefore there is a voltage drop across those 2 points. So that is me being tricky.
So for the first part, it's going to be 5 ohms times I1, but would we add a negative because of the negative, like how you assign the polarity for Vx?
No, so for right now, Vx, let's ignore it entirely, okay?
Okay.
We'll work towards figuring out what the relationship between Vx and our mesh currents is a little bit later. For now, let's just figure out how to define what our mesh currents are and solve for them. So you said 5 ohms times I1. I absolutely agree with that. What's next?
It'd be 16 ohms times I1 minus I2.
All righty. And what's next?
21 ohms times I1 minus I3.
Absolutely correct. Somebody else tell me what's going on with mesh 2. Start here at the bottom left-hand corner and just follow I2 around its clockwise path.
16 ohms, I2 minus I1.
All right, what's next?
Plus 20 ohms times I2.
And what's next?
Plus 25 ohms, I2 minus I3. Equals 0.
All right. So if we tried to write a KVL equation for mesh 3, we would run into trouble because there's a current source in there, right? Now, the problem that we are going to face here is because the current source is on the perimeter of the circuit, there's really not a super mesh path that we can take that avoids us figuring out what the voltage drop across that 7 amp circuit is. So we are not going to do Kirchhoff's voltage law at all because we have a current source, or for mesh 3, because mesh 3 contains a current source that is on the perimeter of the circuit. Instead, we are going to write a current relationship equation. So I can say that 7 amps, the current being supplied by my 7 amp source, how does that relate to my mesh currents? Any thoughts?
Wouldn't it be based on like the directions of I1 and I2 and I3 relative to the 7 amp source?
Absolutely correct. So what's the answer?
I1 will be positive because it's going to go in the same direction as the 7 amp source.
You're doing too much thought.
I1 plus I2 plus I3.
Nope. Also too much. So let's look at it. All right. When I3 is flowing around its clockwise path, when it comes through this bottommost branch containing the 7 amp source, I3 is in the same direction, right?
Yes.
So I3 is 7 amps. Yeah, it's just I3. So the reason why it doesn't have anything to do with I1 or I2 is because those mesh currents I1 and I2 only flow in their circular little boxes. The only mesh current that's flowing through the branch containing the 7 amp source is I3. So I3 is 7 amps. Does that make sense?
It does.
So if I had instead said that the 7 amp source was providing a current that goes from left to right, we would then have just have said that 7 amps is equal to negative I3 because those two currents are in the opposite directions. So I have 3 equations, 3 unknowns. You guys tell me what my answers for I1, I2, and I3 are supposed to be. I'm not going to organize stuff for you. You need to get in the habit of doing it yourself. Or really, it's not even remotely necessary to actually write down all that kind of stuff. What I've written here is good enough for you to punch numbers into your calculator pretty easily because you just add together the coefficients for I1, coefficient for I2, coefficient for I3, etc. Has anybody gotten anything yet?
I got 5.103 amps for I1 and 4.2073 amps for I2, and I3 is 7 amps.
That is exactly what I got as well. So let's bring things home here and figure out how to use these mesh currents to determine our voltage Vx. So somebody asked earlier why I drew this Vx this way. And the answer that I gave, which is true, is to be intentionally confusing or to be tricky. So let me explain by what I mean by that. The voltage Vx is absolutely the difference in electric potential between this point in the circuit and this point in the circuit. That being said, this is all one node that I've just labeled in green, right? Anybody have any problem with me calling that all one node?
No.
Okay. So if the negative polarity terminal is attached to the green node, how is me defining Vx as I've just done it as the voltage drop across the 21 ohm resistor any different than the way that I drew it a moment ago or had it drawn a moment ago? So it isn't. They represent the exact same thing. It's just expressed slightly differently. Okay. So if we understand the concept of voltage, we could easily see then that our voltage Vx, the potential difference between this point and this point, is the exact same thing as the voltage drop over our 21 ohm resistor with a positive polarity terminal on the right and the negative polarity terminal on the left. Knowing that, how do we solve for Vx?
Using Ohm's law?
Using Ohm's law, absolutely. Ohms, which is the resistance. So what's the current flowing into the positive polarity terminal?
I1?
So I1 is part of it,
Minus I3?
minus I3. There we go. So Vx is simply 21 ohms times I1 minus I3. So that would be 21 negative 39.842 volts. All right, so let's recap things here. I'm going to scroll back up through to the very first problem, and we're just going to talk about what we did and then see how we change things whenever we added current sources to the system. All right. So for our first problem, way up here, we had a circuit that contained only voltage sources, all right? So we identified and labeled our meshes. Then we wrote KVL equations for each mesh. Because there was a dependent source, we had to also develop an equation that expressed the controlling variable in terms of our mesh currents, set up a system of equations, and then solved it. Got our answers. A current source into the mix, we had to introduce the concept, or excuse me, when we added a current source that was on the interior of the circuit, we had to introduce the concept of a super mesh, wherein we create a path that avoids having to do KVL directly across that current source, because we cannot express the voltage drop across a current source in terms of our mesh currents, because they're unrelated, right? All of our current sources supply a fixed amount of current regardless of what voltage appears over them. So we had to take our super mesh path, and we also had to develop a current relationship where we expressed the current being supplied by our current source in terms of our mesh currents. For our third problem here, very similar to the second problem, except that our current source was now on the perimeter or the outside of the circuit. Because there's no way for us to draw a super mesh path that avoids us taking the voltage drop over it, we will only have a current relationship. So in summary, anytime that we have a current source in our circuit, and for every current source in our circuit, we should expect to have to write a current relationship equation. If the current source is in the interior of the circuit, we will also have to write a super mesh equation. If the current source is only on the outside, we don't have to write the Kirchhoff's voltage law expression. So let me look at the schedule for this class real quick. For the tentative schedule, mainly I'm looking at the test date. For 2021. All right, so everything was in line with what I have on the syllabus, except that we skipped linearity and superposition and went to nodal and mesh analysis. So our next class meeting will be on linearity and superposition. Legitimately, I don't think that that lecture will take more than 45 minutes. So what I would really like for you guys to do before class on Monday is attempt some of the homework problems from homework set number 6 and homework set number 7 for nodal analysis and mesh analysis. And I'd like to spend maybe 30 to 45 minutes answering questions on these two topics, because A, they're important, and B, it's what you guys are going to try to use for pretty much everything. So I want to make sure that you fully understand it. So I reiterate, I would really like to dedicate the first 45 minutes or so of class on Monday to answering questions regarding nodal and mesh analysis. If you want to shoot me an email saying, hey, Dr. Hartman, could you look at this problem at the beginning of class on Monday, that's a perfectly fine way of doing it, or you can actually volunteer to ask a question at the beginning of class. Either way works for me, but I really think that it's in your best interest that you take a crack at some of these problems, and then if something doesn't make sense, we can discuss it. Does that sound like a plan?
Sounds like a plan.
All righty. Well, I don't have anything else for today. So if there's any questions that you guys would care to ask right now regarding any of the homework assignments or anything else, I'd be happy to answer it. If not, I will see you guys in class on Monday.